Okay. You know what? When I was in college, I was quite complacent. I thought I know everything. So even if I don't, I should be able to learn it pretty soon. And that's how I achieved a bachelor degree. Okay. And several years later, I asked myself, do I really understand epidemiology? Am I a so-called epidemiologist after the training for a master program? And I got a master degree. And after several years, before the oral defense of my PhD, I was quite panicking because I'm not so sure that what I'm talking in my oral defense will be still true after a period of time. And they gave me a PhD. I worried that people might dispute my idea of research and seriously, and the story I was talking in my oral defense would not be true anymore. Yeah, but fortunately, it's still true. I mean, no one found other evidence against my research outcome for my PhD. Today, we are going back to the study design, focusing on cohort study. I know you have some idea about cohort study, right? We've talked about it for many slides in previous lectures. But today I'm going to go into the details about the principle of cohort study and reinforce the concept of cohort study. So you'll learn almost everything about cohort study in today's lecture. So first of all, I have to highlight the dilemma between science and ethical considerations in human subject studies. That's why, for most of the chances, we have to perform observational study. That's because ethical considerations. And cohort study is the best study design, the best study design in observational studies because time is a critical issue for considering study designs. And the cohort study is like that. So you will be able to, at least, you will obey the consideration about the temporal relationship in the judgment or causal relationship. And then I'll go in step forward about how to perform a preliminary data analysis in cohort studies, talking about some characteristics of different cohorts for specific study purposes. We might need to modify the methodology of statistical analysis method based on the cohort involved in the observational study. So that's why I emphasize the importance about the entity of the diseases. We need to know something before we could start to perform studies on those diseases of research interest. Okay, and the most important thing is about how to calculate SIR and SIR. That's the key point for today. Standardized incidence ratio versus standardized rate ratio. That's so-called standardization. This will be the first method you are going to learn about how to control confounders. For the purpose of elucidation on the concept of cohort study, I might need to suggest to you the idea about what is so-called concurrent cohort and birth cohort. There are two different perspectives to look at the cohort in terms of time. Like what I said before, time is important. But looking at the cohort, we might have different aspects, especially when we have a huge cohort follow-up for a long period of time, or so-called long-term follow-up cohort study. They won't be able to look at the data with the concurrent view or the birth cohort view. Then the outcome will be a little bit different. So there are specific skills developed to discriminate the differences between concurrent cohort and birth cohort. And then I'm going to introduce the methods about how to assess the excess risk in cohort studies. And that might be the end of today's lecture because we don't have time. So next week, I will go into the details about how to utilize life table to describe the general mortality in a cohort. It could be as short as a follow-up for a year, a cohort follow-up for almost 100 years. And then I will raise some genuine examples to show you what we can do with the data of a cohort. Dilemma is kind of trade-off. First of all, I have to introduce or say something about Charles Darwin. Everybody knows his story, right? He was the one who generated or proposed the idea about evolution ever. So it's the origin of the modern biology, right? Without evolution, we thought all the creatures were created by blah, 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 right? And you know the story about the beagles, right? He got a chance to travel in Galapagos Islands in Central America. He just performed simply observation and got some idea about the difference, why the species on the islands are a little bit different from each other. He came back from the trip. He wrote a book called Origin of the Species, which was published in 1895. But the idea is that evolution, variability or variation in animals or plants are much bigger than the other things. So it's a fundament for evolution. So if all the creatures are exactly the same, like products from the plants or industrial products are exactly the same, then there's no such a thing for evolution, right? So what happened will be totally by chance. Yeah. But because of the nature of the biology, the variation is so huge, so which make it different. It's not only happen by chance. It could be happen because of variation of some specific characteristics to give the survivors a higher chance to survive for a longer time. Bear those kind of things in mind. So, and also we observe a lot of high level of uncertainty of the measurement in biology. With blood pressure as an example, even if we just do the measurement of blood pressure twice in a minute, it'll be very unlikely to find exact the same measures for blood pressure, right? So it just change all the time. We made some practical and ethical difficulty in the manipulation of biological exposures. It's not very likely to manipulate everything about the exposure for biological studies. Okay, not like what we can do in physics or chemistry research in the laboratory. That's why we need to develop some methodology to deal the issue of the differences other than the exposure we're interested in, which is so-called mostly about confounding control, remember? So what we can do about science here? At least we could ensure the comparability. So in other words, the differences other than the exposure we're interested in has to be dealt with somehow to make them comparable to each other, no matter it's a case control study or cohort study. For cohort study, the exposed group compared to non-exposed group. For case control study, the case group compared to the non or control group. We have to try very hard to maintain the scientific structure of the research. That's something that the epidemiology different from other kind of biological research because they are human beings. So it makes it even more difficult to deal with it for the manipulation of the exposures. But the idea about the ethical issue come up to research or investigations are pretty late. As late as the Helsinki Declaration in 1964, which is the World Medical Association Conference, something like that. And that's the first time people start to think about the ethical issues in human subject studies. Before that, the researchers or clinicians might treat people like animals. They don't really care about their benefit or their comfort. So the idea came up pretty late. 1966, a doctor called Henry Beecher, he published an article in New England Journal of Medicine with the title of Ethics and Clinical Research based on the Helsinki Declaration. That's the origin about and how we take care about the people involved in your research, human subject research. So because of these ethical concerns, in epidemiology, what we can do will be mostly observation and rather than intervention. Intervention means that the exposure will assigned or distributed by researcher. And observe just means we just stand aside and watch what's going on there. We don't try to do anything on those study subjects. So we have to develop many skills to solve the problem raised by the uncontrolled factors, not like what we can do in the lab. So that's so-called confounding. I have give you everything I know about confounding from the lecture last time. So mostly what you are going to learn about the statistical analysis or epidemiological methods or surrounding confounding. Although it's not the major one for biases, but it's very common. It's everywhere, almost every single epidemiological studies. So we need to learn something to deal with it. And actually, maybe 80 to 90% of efforts for epidemiologists are working on the stuff about confounding control. So let's get back to the study design. For most of the chances for a specific study topic, we must start with descriptive epidemiological study first. And what is so-called descriptive epidemiology? It's generally done without a hypothesis specified in advance. In other words, we don't specify the causal relationship between the exposure to the outcome of our interest. But it will be very helpful for us to generate new hypotheses, the descriptive epidemiology studies. And it's often used to detect association only, which may or may not be causal, because the available data might be there. And what you can do is just do the association. Since the purpose is for descriptive, so it might be hard to identify any causal relationship there, but it will be helpful for us to detect association, and then we could generate new hypotheses for a specific exposure to the outcome. And for descriptive epidemiology study, we often use pre-existing data from the government or regularly collected clinical information, something like that. So in other words, for descriptive epidemiological studies, we don't try to get the data for specific purposes, for research purposes. So the association we identify there might be just something happened, a coincidence by chance, or it could be something secondary to each other, like what I suggested in a previous lecture, secondary correlation. We'll be able to find the significance, but they are not the causal relationship at all. So we need to judge it. So relatively, in analytic studies, we have to specify a hypothesis in advance. In other words, like what I said in the consideration of confounding, we specify one specific exposure. We don't know much about it. That's why we need to perform a research to study on that exposure, right? And then we try to collect new data for the purpose of research. So now we could try our best to collect all the information we need for the exposure of interest in a hypothesis and outcome, and also the other independent risk factors, which will be controlled as potential confounders. Okay, so that's the activity or steps we are going to do for analytic studies. Okay, talking about the timing issue in epidemiological study design, like what I have highlighted for several times, it's critical to find a way which is as precise as possible to detect the disease. So it's essential to ask how you define an onset of the disease, of the outcome. So you need to know more about the entity, and also you might need to know something about the clinical practice, about how the diseases were diagnosed. For example, cancer. Generally, we use the information from the pathological report, to define the onset, because cancer is a chronic disease. There's no specific point of time of onset. So in practice, we use the date of the path report as the onset date. What about DM, diabetic mellitus? It might be very difficult again, right? So we might use the report from the laboratory as the onset in practice. But I believe that it happened a long time ago before that, right? Because again, it's a chronic disease. And then we have to consider how to do the measurement of exposures and think about what kind of study design should be used to answer the question I raised in the hypothesis, right? So the thing is about timing. So there are two directions, retrospective or prospective. So in case control study, it will be mostly retrospective or cross-sectional. When you're performing study in a cross-sectional study design, you could ask what happened before. Or you could ask him or her something generally don't change, like gender, right? Date of birth, those kind of things doesn't change. Okay, and smoking habit, drinking problem, something like that. So for case control study, mostly retrospective, but it could be prospective somehow. I'm going to tell you why and how it works in that way in a lecture about case control study in the following weeks. Okay, but for cohort study, it'll be basically prospective. In other words, we try to find a group of people who are at risk for the outcome we are interested in, but they may or may not exposed to the exposure. And then we follow up to see what happened for a period of time for the incidence of diseases, right? But it could be retrospective occasionally. Why? Because nowadays it's an era of the big data, right? So we have a lot of huge databases available for the purpose of research. Although they were not collected for the purpose of research, but the records are there. So if you are performing a research based on hospitalization records or national health insurance records, then it could be retrospective in that way. Okay. And it's very expensive if you want to generate a new cohort by yourself. You might need millions of dollars and spend decades to get those outcomes. So in observational study, the exposure status is often self-selective, which is increase the chance of the various biases, especially for confounding. Don't jump into, or it must be selection bias. It'll be mostly about confounding, actually. It's not so easy to do the judgment at this point. But I'm going to tell you how to discriminate selection bias and confounding. So whenever you have no idea about what kind of bias it is, confounding is the answer, 95% true. Okay? Because people choose the exposure, they decide to smoke or drink, right, themselves. And behind it, there are a lot of characteristics which is about it. Like smoking is about gender, it's about socioeconomic status, it's about occupation. There are a lot of things behind the exposure. So be mostly about confounding. Okay? So we need to develop something to deal with it, especially for observational studies. Okay. So here is the diagram about the prototype of cohort study design. So first of all, we have to specify a study population. But we don't have the efforts, we don't have the sufficient number and manpower to follow up every single one in that study population. So what you can do is to try to generate a cohort which is representative to the study population somehow. Okay? But we did not perform anything like randomization, so they just choose to expose to something or not expose to something. And then we'll follow up to see what happened for the disease afterwards. This is a prototype of cohort study design. It's very straightforward, right? It's natural. That's what happened every single day in human being. But the key point is that we did not do anything about the exposure. We don't assign them to those people. So the only thing we can do is to write down what the exposure status at the starting point and measure the factors who might matter to make them different for these two comparison groups, which are confounders. Sorry. Okay, so first of all, I have to emphasize it again. In a cohort, the study subjects who are not at risk has to be excluded from the study population in the very beginning. So in other words, they would not be counted in the denominator in a further calculation or research. Okay, in a cohort, then we could define it as a group of people who share a common experience or condition. Common experiences, birth cohort, so people were born in the same year or in the same month or even in the same year, sorry. or in the same year and month. That's a birth cohort. Or a group of people who get married in the same year or in the same season, and they are in the same marriage cohort. Or if people choose to work in the same occupation, then they will be a group of cohort again. So you and your classmates is a cohort, right? The GHP program 2020, cohort, that's you. So you share the same experiences, right? As a student in PhD, Global Health Program, right, in NTU. Condition, why is it about condition? If we consider disease as exposure, like diabetes, if you want to know what happened for the people with or without diabetes, then condition could be an exposure in that kind of consideration. That's chronic disease epidemiology or clinical epidemiology. So the cohorts are formed based on exposure status at the beginning of follow-up. So we have to specify a point and then try to identify the exposure status and then follow up. That's very straightforward again. So the exposed and not exposed group may not necessarily reflect the true exposure proportion in the population. So if you want to perform a study that the exposure is rare, then if you don't do anything about it, then eventually most of the study subject in a cohort will be non-exposed. So there will be so-called statistical power issue. You might not be able to identify sufficient number of the people with the incidence of disease eventually. So you might be able to get a group of people who are all exposed to something, which might take 90% of the people who exposed to that specific risk factor at that time. And then you just need to take the maybe 1% of people who are not exposed to that specific risk factor and then follow up. So it works. It could work in that way, especially when the exposure is rare. So it still makes sense. You don't need to follow up every single one. So there are a lot of the advantage and also disadvantage for cohort study design. Let's talk about the strength about it. First of all, in cohort study, we are pretty sure the exposure is known to precede the outcome. So it satisfies the temporal relation, which is the only necessary one in the judgment of causality. Remember? Okay, so that's the best part about the cohort study design. And also, we could directly measure the incidence of disease if we could collect the information to calculate no matter cumulative incidence or incidence density, we'll be able to find incidence. Because incidence will be very useful for etiological studies. Okay. And also we could calculate the rate ratio directly. We don't need to use the idea of odds, AD over VC, blah, blah, like case control study. It would be very straightforward to do the estimation of relative risk by rate ratio. And also, with the cohort in hand, that's the dream of every single epidemiologist. You have a huge cohort in your hands. They could perform the study with multiple outcomes in the same study. With the smoking as an example, if you follow up a group of people for a long time, and you could perform the study for different kinds of cancer or different kinds of respiratory diseases, almost all the diseases, right? And nowadays, it happens a lot that one exposure might cause different kinds of diseases. But of course, there are some weaknesses about the cohort study design. First of all, it might be inefficient for rare or delayed outcomes. If the induction or incubation period is as long as more than 10 years, then you might need to follow up this group of people for more than 10 years. Or if the outcome is really rare, then you might not have sufficient statistical power to identify the significance of the exposure, of the effect of the exposure. And the other thing is that prospective cohort study could be very expensive. So it's very unlikely to get sufficient funding to do that. Talking about the data analysis, like what I suggested before, is very straightforward. So since it's a cohort study, so the starting point is here. Exposed, non-exposed group, and follow up to see what happened. let's say that we have A plus B, is the total number of people who are exposed to something, and A of them got the disease during the follow-up period. Could be 1 year, could be 10 years. And for the non-exposed group, we got C plus D. And C is the number of people who got the disease during the follow-up period. So this is the consideration of cumulative incidence, right? So we could calculate cumulative incidence for the exposed group, and here's the incidence for the non-exposed group. So it's very straightforward that we could calculate the rate ratio, which is estimation for relative risk in cohort studies, right? A divided by A plus B, there. That's the incidence for the exposed group. And here is the incidence of non-exposed group. But in this calculation, we did not consider anything else other than exposure we're interested in, right? So we call it a crude estimation or unadjusted estimation of the relative risk. But without considering other risk factors other than the exposure status, we cannot make a final conclusion yet, unless we have to go through the process about the measurement and adjustment for confounders. Then we could make a better conclusion based on the adjusted estimation of the relative risk. Okay, so it's just crude, unadjusted, but that's the way we do the calculation of rate ratio for cohort studies. No matter for cumulative incidence or incidence density, that'll be the same because the ratio, so the unit will be deleted in the process of calculation. Okay, so that's how we get a single simple indication about the effect of the exposure within this group of people. Okay, so there are some challenges we have to face when we are trying to conduct cohort studies. The first one is non-response. Since you need to follow up a group of people, some of them just stop responding to your research, or they just stop taking your call, or just throw your questionnaire to the garbage can or trash can, or so-called loss to follow up, or attrition. People just disappeared without a reason. And it happened frequently, but often non-random. In other words, they disappear for a specific reason. There might be people with a very high socioeconomic status or very low socioeconomic status. And if the reason why they were lost to follow up and the factor is related to the outcome, then it's a selection bias. Okay. So even if that happened in random, then those people who stayed to the end of research, there will be a reason for confounding. Ideally, the response rate should be like at least 70% or something. If it's as low as 30%, then people will question or dispute your research outcome, or if it's too many. Okay, and also the exposure status change over time. People might start to smoke, even if he or she was a non-smoker in the very beginning, right? Or he or she might quit the cigarette and start it again. It happens a lot, right? So that will cause the problem, so-called misclassification of exposure, which is a kind of information bias. Okay, the name is not really important, but you need to know that it's a kind of information bias. Then we might need to deal with it somehow for the major exposure of interest. Okay, and like what I said before, if it's rare disease for the outcome or rare exposure, then you need to have a huge or bigger sample size for the cohort to generate sufficient statistical power to identify the differences between the comparison groups. And the other thing is that since we need to follow up a group of people for a long time, the quality of detection system will be critical. What is so-called case detection system or so-called surveillance system? That's the way we identify important diseases in a population, like cancer or stroke, case registry system. Then it's important to ensure that the quality of the case detection system is okay from the beginning to the end, which doesn't change too much. But for most of the time, it's improving gradually, right? So what are we going to do with previous or older cases, because we don't have sufficient information about the quality of the diagnosis. And also the disease diagnostic criteria might change over time. In Taiwan, we were using ICD-9, but now have transferred to ICD-10. But ICD-9 is not identical to ICD-10. Sometimes, for some diseases, it's just one disease becomes 3, or 3 diseases become to 1. For a lot of chances, they are not identical. You cannot just group or regroup them to make the diagnosis the same. So analytic bias is something happened, especially when you have when the statistician has some idea about the exposure status. Okay, so it's a potential selection bias because the one who performed the statistical analysis just has some idea about it, about the exposure status. So the outcome might be misleading. Talking about different kind of the study cohort, it depends on the study topic. If you are interested in the research about mental health, the good point is that the follow-up period is quite short. In 9 months, you will be able to identify the outcome, right, to give the birth. And also, in the reimbursement system in national health insurance, especially in Taiwan, we have the regular practice in medical care system to provide 3 times the ultrasound scan, I think, and allow a whole bunch of the laboratory examinations for the purpose of the so-called antenatal examinations to identify the exposure and we are interested in, and the outcome will be it's quite quick to get the outcome for a cohort in the maternal health. So it makes it pretty easy to perform a study with a pregnant woman, right? In 9 months, you'll be able to identify the outcome, the adverse outcome for pregnancy. If you want to perform a study about cancer, the key point is that generally speaking, the exposure we are interested in about cancer will generally cause the multiple outcomes. I mean, the same exposure might cause different kind of outcomes. Smoking will be a good example. It's pretty true that smoking are related to elevated risks of many different kinds of cancer. Breast cancer, lung cancer, liver cancer, colorectal cancers. For occupational study, people are studying on the rare but the specific exposures in a specific industry. With the example of the vinyl chloride monomer, or VCM, which is the unit for plastics. And it's not available in the nature, so it's artificial. It's totally industrial thing. But it will cause a very specific kind of the cancer called the hepatic angiosarcoma. Okay, then it'll be easy to identify the causal relationship between the exposure to vinyl chloride monomer to that specific kind of liver cancer. But if you try to perform occupational study, you might need to consider what kind of comparison group you should use. It could be intra-comparison, which means that we just compare the people exposed to something in the same company to the ones who are not exposed to that exposure. For the ones who are exposed to VCM, they could compare to the people who work in the human resources, for example, or accounting department, who are not exposed to the chemical. Okay, then we could get information about those group of people, and we could have a better chance to control the potential confounders. Right? We could ask them about how about your age, gender, education level, and their exposure outside of the factory, and the family history of the medical blah blah blah, a lot of things, right? But sometimes we don't have a chance to go to perform that kind of comparison. We have no choice to do extra comparison. In other words, we have to compare to those people who are not working in that industry. There'll be a lot of more challenges to get those information about confounders for the purpose of confounding control, right? So that's why we need to use, that's one of the reasons we have to use the indirect standardization to compare a smaller but specific group of people to the general population. Okay, that's so-called extra comparison. That's why we developed indirect standardization methods. Okay, and if you are using the health insurance data to perform a retrospective cohort study, then the good point is that it's population-based cohort. So there's no such a problem of representativeness anymore. Yeah, but the problem is that the data was not collected for the purpose of research. So a lot of things might not be available or incomplete for your research. So the consideration will be different. And also in the health insurance data set, issues or information about environment exposure or smoking habit or lifestyle issues might not be available there, right? Or BMI, they are very important, but it's not available. SIR is the abbreviation of standardized incidence ratio, okay? But the incidence here could be replaced by mortality or admission rate. So it could be SIR, also it could be SMR or SAR. But no matter what kind of S something R, it's indirect standardization. It's a ratio, okay? And SRR is a standardized relative risk. So it's a so-called direct standardization. I'll tell you why it's indirect or direct standardization. Here's an example of a cohort study with 3 comparison groups. We have 5,000 people who are non-smoker, 5,000 people who are light smoker, and 5,000 people who are heavy smoker. Okay, and we follow for a period of time. And eventually, in a group of non-smokers, we got 1,000 of people got the disease, or lung cancer maybe. Okay, and 2,400 for the light smoking group. Okay, and the heavy smoking group, 2,100. Okay, but before we start to do anything, let's observe what's going on about the age structure. I simplify the scenario, okay? So here for the heavy smoking group, 4,000 people younger than 50 and 1,000 people older than 50. And compared to this group of people, that group is younger, right? 4,000, 1,000. 1,000, 4,000 so is younger for that group. So since age is a non-independent risk factor, it has to be addressed somehow to deal with the confounding from age. Okay? So, and here's the non-smoking group, half-half, which is between these two. So now let's use the non-smoking group as so-called reference group or standard population. Then we could do the calculation for SIR and also SRR. Also, crude means that if we don't adjust anything, if we don't take care of the age structure, so it's simply, the crude RR is simply this, 0.42, which is the number divided by the crude. So this is reference group. So this is the crude relative risk or crude rate ratio. And also this divided by that, 2.4. But it's weird and also intuitive that light smoking people got a higher risk compared to the heavy smoker. And people may argue that, oh, that's because they are younger, right? Then we have to adjust the issue about age structure to have a better comparison. Okay, that's the background of the story. Okay, so now how are we going to get the 3 here? For the calculation of SIR, we start with the equation here. O means the total observed number of people getting the disease, which is 2,100, right? That's what happened in the heavy smoking group, 2,100. That's the observed number. Divided by the expected number of the cases. Okay, how are we going to do it? Because indirect standardization, we are going to use the age structure of the cohort or the exposed group we are interested in and the rate from the reference group or standard population, which is 0.1 or 0.3, and 0.1 and 0.3. That's how I get it. So now I have 4,000 people in the younger age group of heavy smoking, 4,000, right? And 0.1 is a number here from the standard population. Okay, and again, 1,000 times 0.3. So we could get the expected number would be 400 plus 300, which is 700. The standardized incidence ratio would be 3. Okay? Okay, so do you want to do it about yourself, about how you can get a 1.85? Exact the same process. Using the population here, and the rate from the standard population, and O divided by E. You will get 1.85. Okay. So now we want to calculate the SIR for the lighter smoking group, right? The observed divided by expected. The observed number of people who got the disease will be 2,400, right? And then the expected, you have to use the people, number of people in the younger age group, which is 1,000, right? For older age group of 4,000. We just apply the population here and the rates from the standard population. So the observed is 2,400, and the expected will be 100 plus 120, right? This works like a rule. We use the rule to measure these two and do a better comparison, okay? So it'll be 2,400 to 1,300, 1.85, right? Okay, that's SIR. Okay, I'll give you some more example next week, so don't worry too much. You just need to remember that SIR is observed number, sorry, it's kind of loud, divided by expected number. And you have to use the structure of your own research group and the rates from the standard population. That's the key point you have to remember. SIR. Now let's move on to SRR. It's also a method to adjust for age structure, but in a reverse way. We are going to use the rate from the group of people you are interested in, and the population structure from the standard population. That's the other way around, right? So over the 5,000 people, we have 2,500, which is the number of people here, right? And the rate is here from the study group you are interested in. So it's 2,050 times 0.4 here. Okay, and the other 2,500 and 0.5 is from here. So now we are using the rate from the group of people in our cohort with a heavy smoking status. Okay, and here is simply the original rate here of the target population. So after the calculation, 2.25, because they are the same, so deleted, eliminated, 2.25. Okay, so you have 2 minutes to do the calculation here for the SRR for the light smoking compared to the non-smoking group. So it will be L. That's the other way around. For the direct standardization, we use the structure, age structure, but the rate. And in the indirect standardization, I use this structure and the rate from the standard population. So it's the other way around, right? Sometimes not feasible, not available, so we have no choice to use SIR to replace SRR. And there are some limitations. Yeah, I'll show you how and why in the following slides. You just need to know there are two different kind of ways for age structure adjustment to consider age as a confounder. This is so-called standardization. Both of them are pretty useful, but in different situations. When we are comparing a smaller group of people with a specific exposure to a general population, we need to use SIR. If we compare our research outcome for your study to another study somewhere else, or every country need to compare the incidence rate for cancers, for example, they need to use direct standardization for the purpose of international comparison. Do you need me to show you how to do the calculation for SRRL for this group compared to this group? So we just apply the structure, right? So I only need to change the rate here. So it'll be 0.4, right, for the light smoking group. 0.4 and 0.5. Oh yeah, it's exact the same number. Yeah. Okay, that's how we got exact the same number here, right? 2.25. Yeah, but actually the process is different. I mean the resource of the source of the number are different. Okay. So now the problem is y is different. 3, of course, is higher too, compared to the reference group, right? 3 times higher. It's an estimation of relative risk with adjustment for age structure at 1.85. But 2.25, 2.25. So comparing to the reference group, they're the same. Which one is correct? SRR is correct. Because the way we perform the adjustment by standardized rate ratio is a real adjustment. So in other words, we have tried to make the structure, age structure exact the same because the process there, right? We use the structure. But for the calculation of SIR, we actually applied different age structure. It's younger, older. So it makes sense to compare this to this, or this to this, but it doesn't make any sense to compare this to that. So actually they are the same after the adjustment to age structure. Okay? But SIR is still useful, sometimes in specific situations. So in summary, SIR are not comparable to each other. That's why it's so-called indirect standardization. Okay? It only makes sense to compare to the reference group, or so-called standard population. Okay? For the group you are interested in, the target population compared to the standard population. So because we use the different target population structures. So that's why we call it the indirect. Okay. In contrast to SIR, SRR are comparable to each other. So it'll be very useful for international comparison or comparison of your research outcome to others' research outcome. Okay, or across the studies. So if but they need to use the same standard population. Then they are comparable to each other. So that's why every 10 years, WHO just announced the national age structure for the world population. So everybody just use the WHO world standard population to do the direct standardization for the adjustment for age structure. Then they are comparable to each other. Okay? So whenever we're talking about age-adjusted cancer rate for breast cancer, for example, which means they use the WHO world population. Okay, then we don't need to worry about the differences of age structure among the different countries for the purpose of better comparison. Okay, you cannot say that in Taiwan people are older, or in Korea people are older, in Europe, in America older, so that's why they got higher. Now it's not an issue. We have adjusted the age structure, right? So age cannot be an alternative explanation for such outcomes. Age has to be considered as a confounder before we can make a better conclusion or final conclusion. Because age and gender is really unlikely to be not related to any health events. Yeah, so they are essential things to be adjusted. So the key point is SIR is not equal to SRR. That has to be done for different purposes. SIR is for international comparison. SRR is to compare a smaller group to the general population. Okay? Although the material are the same, age-specific mortality, age-specific incidence, and age structure, right? But the result, the source are different. the information given is different in the process. Okay. The other thing is about the way to look at the cohort. If you have a long-term follow-up, here's the real data, which is confusing because the issue about concurrent cohort and the birth cohort. Let's look at the solid line here. Okay, the solid line. The one at the top means that it's the observation done in 1960. Okay, and this is the observation done in 1950. So in other words, that's the incidence rate of it's lung cancer, I think. Yeah, it's lung cancer. So we do the observation for every single one from age 35 to age 85. So in other words, we found out that the incidence rate of lung cancer is increasing every 10 years, right? That's what we found. But it's weird that it's bending down, right? Yeah, because after World War II, people start to smoke a lot in America. So it's true that it's increasing, no matter which age group. Right? But it's why it's weird that older people got lower rate compared to the. Okay, then this is so-called the concurrent view on those cohort. Okay, but if we look at exact the same data in different view, if we use the birth cohort, let's look at the dashed line. The dashed line, this one first. These are the group of people who were born in 1885 to 1854. This is a group of people who were born 1855 to 1864. And this is a group of people who were born in 1986 to 1865 to 74. Okay? And then you will find out that the incidence rate increase along with age, nothing bending down. Which one's correct? Birth cohort makes more sense, or concurrent cohort makes more sense? Do you want to vote? This is democracy. Okay, the one who supports the concurrent view of the cohort? No? Great. What about the birth cohort? Yes, birth cohort makes more sense. Because we know that since the major risk factor for lung cancer is industrialization, right? Air pollution and smoking. So there's no reason it's just bending down. The incidence rate of mortality for lung cancer just decrease along with age. But why is bending down? That's because there's the combination of the people from different birth cohort. So it's something mixing up with the age period cohort effect. Okay. But you don't need to worry too much. There's nothing about calculation here. You just need to know that if possible, birth cohort makes more sense. Okay? And it's very difficult to deal with the mix-up effect, the mixing effect of age period cohort effects. Okay? I just want to tell you that anything about timing is difficult to deal with in cohort studies. If possible, use the birth cohort. It will give you a better view about the answer. So in the last 10 minutes, I want to introduce some indicators which is useful for you to show the excess risk in cohort studies. The first one is rate ratio. We already learned it, right? So in cohort study, it's a rate ratio, which is the estimation for relative risk. The second thing is the rate differences, like what. But in cohort study, we also call the rate differences attributable rate. I will show you the formula in the following slides. And also we could do the calculation of AR%, which is abbreviation of attributable rate percent. And we could also do the calculation of population attributable rate and population attributable rate percent. Okay, you already know the previous ones, right? So now the key point is this AR% and the PAR%. You need to know how to calculate it and how to explain it. That's very important. And generally, we are showing these two indicators as the major output in cohort studies. So R is defined as the ratio of risk between exposed and non-exposed group in cohort studies, right? So you already know that. And the RD is the difference of risk, okay? Okay, and AR, attributable rate, which is the calculation is defined as the incidence of disease due to exposure among exposed individuals. So it's exactly the same as RD. But in cohort study, we call it attributable rate. So it's very straightforward. The incidence of exposed group subtract the incidence group of non-exposed group. The next one is not so straightforward. AR percent. It's defined as the percentage of disease in exposed individuals due to exposure. So this is AR, right? And divided by the incidence rate of the exposed group. In other words, that's the extra risk, right? As a proportion of the total incidence rate of the exposed group. Or what's the percentage of the extra risk could be explained by the exposure. Right? And why is this? I can show you. So IE minus I0 divided by IE. Okay. So if we divide IE on the both sides, it will be IE, sorry, I0, I0, okay, by the IE, I0. I divide both sides with I0 here. Okay, then become IE I0 minus IO IO, which is 1, right? And this is IE divided by I0. This is RR, right? Relative risk, incidence of the exposed group divided by the incidence of non-exposed group. So become R minus 1 divided by R. It's a simplified way. You don't need to remember such kind of thing. But the key point is that, so since RR here, it's the rate ratio. It could be replaced by odds ratio. So even if the result is from odds ratio, from case control study, we can still use the formula to generate the attributable rate percent, right? So now it becomes applicable to case control studies because of the simplification of the formula. But about how to explain it, that's the percentage of disease because of the exposure or caused by the exposure. So it's a percentage. People might argue that, but not everybody is smoking in the population. So it's kind of too extreme, right? It might be exaggerated, right? So some people suggest that, okay, then let's do it with the population attributable rate, which is defined as the risk of disease incidence in the population as a whole. In other words, some people are smokers, some people are non-smokers. Some people might expose to something we're interested in, some people might not. So that's the I here, capital I, for the population, minus the I0. That's the incidence of those people who don't smoke or not exposed to it. That's called PAR. Okay. Now the key point is the PAR percent. It's the percent of disease incidence in the population as a whole due to the exposure we are interested in. So it's I minus I0 divided by I, like what we did for PR percent, right? So it's also called etiological fraction. In other words, if we initiate a quit smoking movement in the society, okay, then what's the percentage of the lung cancer could be eliminated? Okay, this is more realistic, more close to the real world, right? But AR percent is kind of too extreme. It's the ideal world. Okay, it's approximate to AR percent times the PC, and PC is the proportion of cases in the population who are exposed to cohort studies, or the proportion are exposed in case group in case control studies. In other words, with this, the idea is extendable to case control studies, but you don't need to worry too much about this. This is true under a lot of assumption only. But you need to know how to do the calculation and how to explain it. That's the key point for PAR percent. Again, let me emphasize it again. So PAR percent means that if we could do something to eliminate the exposure of something which might be the cause of the disease in a population, then what is the percentage of cases could be eliminated because of it? That's why you call it etiological fraction. So in other words, if there are more people exposed to the smoking as an example, then the proportion will be higher, right? If the effect of smoking is so strong to make people sick, then it will be higher again, right? But if the effect is weak or the proportion of smokers is small in a population, then the proportion will be small, right? So it's more applicable and make more sense to convince the politician or policymakers, right, about why we need to ban cigarette in the population. It would be more effective if we could do the movement or initiate the movement in a population with a higher smoking rate, right? Okay, so it makes sense in that way. Personal insight. Cohort study is the fundament for all epidemiology study designs. Actually, no matter what kind of study design, we are trying to mimic what's happening in cohort studies. No matter it's a case control study, like what we said, we use the idea of odds ratio to mimic the estimation of a rate ratio, right? Remember? And for randomized control trial, it's kind of artificial cohort study, right? They manipulate or assign the exposure to people, right? But actually, it's still a cohort study. The only difference is we could assign the exposure or intervention to those group of people. So it's important to understand what's going on for cohort study as a fundament to understand what's going on for the other study designs. And cohort study are not always applicable because it's too expensive, it takes too much time. So if possible, if the data is available and sufficient and complete enough, retrospective cohort study might be a better choice, which is the database, hospital record or health records or national health insurance records would be better. And the concept of person years is important in cohort studies. If you have the information about the exact starting point of follow-up and the exact time of the diagnosis, the perfect. But sometimes we have no choice to use cumulative incidence as a substitution for the calculation of incidence density. Data availability is the key issue for extra comparison. If the cohort in our hands is a small group of people, then what we need to do, at least we need to adjust for age and gender structure, right? For the purpose of confounding control. What about the other important risk factors like BMI, like chronic disease? You need to have information of the general population to perform the extra comparison by the method of standardization, right? But for most of the cases, it's not available. Smoking status, physical activity, blah, blah, blah. So that's why for extra comparison or indirect standardization, we only use it for the adjustment for something available for both sides, age and gender structure, and maybe ethnicity. That's it. Nothing more we can do that. But it will be a great starting point as the preliminary data analysis, at least adjusted for age and gender structure. That's the first step to make a better conclusion. Okay. And anything about time in epi is hard to deal with. It's challenging, it's difficult. So pay more attention. If you want to learn advanced statistical method about timing or advanced epidemiological methods, timing is something you need to consider. Read my lips. We only do observation for most of the time because of the ethical issues. Thus, confounding those bothersome factors is critical in epidemiology. But if you could do it to sort it out together with study design, that will be even better. Okay? Consider the issue about confounding control at the stage of study design. That will be better. Like matching. We are going to talk about it in following lectures. You have to put them together. Then you have a better solution. And don't get confused with the prospective, retrospective issues in study design. Sometimes in the published articles, they said that we are performing a retrospective course, like blah, blah, blah. Or they are saying, we are performing a prospective course study. But it's not true. If you look into the way they perform the study, how they define the timing issue, it's not like what they say at all, even in the published articles. So it's critical to know how to identify the study design by the timing issues. And I have to emphasize again, SIR is not to SRR, not equal to SRR. If possible, we prefer to use SRR rather than SIR. But SIR might be the first step to compare a smaller group of people for our research purpose to the general population. Ways to think. Okay, you can think it at home. We got the data of the risk factors A, B, and C for calculating AR% within an epi study. It turned out that AR% were 30%, 25%, and 65% for A, B, and C. It could be even more, right? But these three might be the major ones as a risk factor for the disease in our research. But the sum of the AR% was 120%. How could it be possible? Does it make any sense? What happened to those 20%, extra 20%? Eaten by your dog or swallowed by a black hole? If A, B, and C is actually the only three risk factors to the disease, then the sum should be 100. If that's the reality, that's the nature of the disease, why is it not 100%? If it's less than 100%, we could say, oh, there might be some other kinds of unknown risk factors. But now it's more than 100. That's ridiculous, right? It doesn't make any sense. Is there something wrong with the story? One of the potential explanations which makes sense is the interaction. There are something conflicting or offsets among these factors. So the answer, one of the answers which makes sense is interaction. There are some interaction going on among these three factors. Okay, so the effect of A might be offsetted by factor B or C. Okay, interaction. Okay, thank you.